everybody, and welcome to Fluid Mechanics. Fluid mechanics is, I think, very interesting. It's one of my favorite subtopics of science and engineering. Okay. And one of the reasons I like it is because it helps us to understand a lot of different things about the world, including piping systems, any kind of system with pumps and pipes, like the plumbing in your house, or the municipal water systems, or things like a chemical plant piping system, because in a chemical plant, you have a lot of different liquids and gases that you need to move around to the right place, and you have to be able to understand pumps and piping in order to do that. Or even something like the cooling system on a nuclear power plant. That is a very fluid mechanics sort of application. There's other things as well, though, like hydropower, such as dams, or wind power, too, is an application of fluid mechanics. So it touches on energy engineering. And it touches on bioengineering. It helps us to understand how fluids like blood or like air travel through our body. And this right here is what's called a computational fluid dynamics simulation of a heart with a mechanical valve. Right? Okay. So that is a computer simulation built on a mathematical model based off of the physics of fluid mechanics that shows us that. And the color right there is the velocity of the blood. And so that helps us understand how the valve changes the flow of blood through the heart. Or modeling smog in a city. There's a lot of applications to environmental engineering with air pollution and water pollution. All have to do with fluid mechanics. Or modeling a plane in a wind tunnel, for example. Mechanical engineers and aerospace engineers especially know a lot about fluid mechanics because the way that air flows around an airplane or a car or anything else is going to have a lot of effect on how it flies and how it performs. Fluid mechanics helps us understand that. Okay, so what are mechanics? Does anyone know off the top of their head the sort of technical definition of mechanics? Like you've taken a mechanics class before.
You got it.
Okay. All right. So does anyone remember, you have taken a class in your past, probably, that was called mechanics, or it had mechanics in the name. Does anyone remember what that class was?
Is it just like something like mechanics?
Your basic physics. Your basic physics class that you took starting off was probably called mechanics. Maybe not if you did it in high school. The BYU first physics class 121. It has mechanics in the title. Mechanics is the physics of forces and of motion. So forces, motion, and energy, how they all interrelate. Forces cause motion, things like that. And what is a fluid? What would you say a fluid is?
Anything that's not a solid?
Anything that's not a solid? That's pretty good.
Or energy.
I'm sorry, could you repeat that?
Not a solid or energy.
Not a solid or energy. Okay, that's a pretty good definition. It describes some states of matter. Usually a fluid is a kind of matter. There is a technical definition that you will find in your textbook or any textbook you look at. And that definition is a substance which deforms continuously under an applied shear stress. What does that mean? So stress. looking back to physics in your mechanics classes you've had before, what is a stress?
A force?
It is a force applied over an area. Okay. So a force applied over an area is a stress. And the stress that you're probably most familiar with is normal stress. So that is stress that acts in so the force acts in the normal direction to whatever plane the stress is acting on.
Is there a difference?
And that's pressure. So pressure is normal stress. And one thing I want you to do is I want you to, and I can't see most of you, so I'm just going to trust that you're going to do this with me wherever you are. Okay, take your hand, take your fist, push into it. Okay, do you feel pressure? Right, you feel pressure. So your hand is pushing normal to the direction of this hand, and so that creates pressure. Right. But then you can also have shear stress, and shear stress is when the force is acting in the shear direction. So everyone do this. All right, do you feel friction? Okay, so shear stress happens when the force is acting in the normal direction to whatever plane we're talking about. And that shear stress is associated with friction. I want you to put a pin in that, keep that in your brain. Normal stress, pressure, shear stress, friction. I also want you to notice that the shear stress we are representing with this Greek letter tau. And tau is the most common symbol for stress in general. Okay. So what does it mean to deform continuously under an applied shear stress? Let's say you have a solid, I'll use this book, right? And I'm gonna apply a shear stress to it, and it deforms a little bit. You know, it changes its shape a little bit, but then it stops. It does not deform continuously. And then obviously if you rub against your desk or your table or something, then you will see it doesn't seem to deform at all. Okay? But now think of the air. The air around you is a fluid. And so when I apply a shear stress to it by rubbing it, it just deforms continuously around it. It never stops moving, deforming, changing its shape. The same as imagine trailing your hand through water. It would be the same thing. Okay, normal stress presses, shear stress rubs. So fluid, technically any substance which deforms continuously under an applied shear stress, but simply what that means is anything that flows, because that was basically what I was saying when I was saying the air will continuously move around the shear stress you applied, is that it flows. And that's mostly liquids and gases, which is why I believe it was Kyle said anything but a solid, right? Liquids, gases, plasmas, sort of. But sometimes something can be a fluid that doesn't seem obvious. So for example, silly putty, right? So silly putty is very thick, but you will find this is a time-lapse video of silly putty. So when we look at it over time, it flows just like water or just like a simpler liquid. And watch that again. By the way, what is the shear stress on that silly putty? Where's it coming from?
Gravity.
Gravity. The shear stress on that silly putty is coming from gravity. And flame. So flames are the hot gases that rise from a fire. There's a reaction happening in them. I want you to look at this flame video. You can see it, it's flowing, right? Flames flow. So flame is a fluid as well. So sometimes things can be fluids that are somewhat not obvious. By the way, that video comes from Dr. Fry here in the chemical engineering department. He studies combustion engineering and fire. Dr. Lignell does computational fluid dynamics modeling of combusting flows, which means fire. It's neat. Now let's take a break for some class business.